Well, I'm glad those of you that can make it safely here got here, and yeah, I got my own little driving story this morning. First time I've ever actually ended up in a ditch. I've never, all the miles I've driven in winter weather, and I've never ended up in a ditch. But this morning, sure enough, that's what happens when they give you a Dodge Challenger on a snowy day at the rental car place. So probably should have turned it back on them and said, no, I think I'll take a different car. But so I barely made it out of the ditch, but I was able to get here. So anyway, made it on time, believe it or not, despite that. So I'm here today to talk about demand response, snapback, and energy savings, and the relationship between them. And we did a study for the Minnesota State Department or Division of Energy Resources, and we looked at these particular things and how utilities can leverage these and how we can quantify these different items. And my clicker decided to stop working on me. There we go. All right, yeah. Okay, finally got that working. So here I just wanted to acknowledge some people that really helped, people and entities really helped out with this. Of course, the Minnesota Department of Commerce Division of Energy Resources, who funded the study. Ralph Dickinson and Bryce Dvorak, who work with me at Michaels Energy. They helped quite a bit in developing this. And then two utilities really helped us out and provided data that was fundamental to the research. They asked to remain anonymous, so I'm going to keep them anonymous, but they were nonetheless very instrumental. So I just wanted to quickly talk about Michaels Energy, the company I work for. We're out of La Crosse, Wisconsin, and we do a lot of work for utilities. Sure, many of you are aware of us that work in this region. We do a lot of custom rebate processing and analysis, along with measurement and verification, and a bunch of other DSM program support, director commissioning for commercial industrial customers, and new construction programs, program evaluation, technical reference manual work. We do a lot of that as well. So we do a wide range of things, so I just wanted to quick talk about Michaels. So this is kind of the outline of what I'll be talking about today. Going through kind of the report I created, which is, I brought with me a copy, but this will eventually be made available by the state. We wrote a final report showing the results of our study, and this is kind of step-by-step through the key elements of that report and covering the main different things we looked at, and I'm trying to summarize it here for you guys to get an idea of what the report is without reading all 45 pages of the report. So the first question I want to ask is, what is demand response? It's utility load relief on peak load days. And there are many different ways of performing demand response. You can do direct load control, where you control the customer's equipment, shut it down, or just cycle it on and off as needed. There's programmable communicating thermostats. This is where the utility will give the customer, residential customers primarily, give them thermostats that the utility can control the temperature of and set the temperatures back on those peak days. And then there's interruption of service, or just simply stopping the source of power to that customer during the peak period, and then having the customer have to address that and deal with that load reduction. So when and for how long? Often it's, most commonly it's hot weekdays in summertime, July, August, when cooling loads are at their highest. And we found from our research that the average demand response event lasts about 7.5 hours, and a rough time frame is 1 p.m. to 7:30 p.m. Something like that. Late afternoon to early evening hours are the most common. Now I'm going to talk a little bit about what snapback is. And there's some different definitions I found. I just kind of Googled snapback to see what would come up. This was the most popular answer, which I didn't wear. I wore these as a kid, but I was not aware that those were called snapback hats. So that was one. Another one, some of these are kind of small, hard to read, but a sudden rebound or change in direction, to make a quick or vigorous recovery. And there's even one here that's even smaller, but it's from writers, television, and movies. It's a plot device used where you snap back to, you reset the entire plot after, say, a television episode where someone dies. The next episode, everything's back to normal. So that's another definition of snapback. But none of these are the ones, of course, we're talking about today. We're more interested in energy than hats. And so we're talking about after demand response event, all your set points for if you change the set points in the building, they all come back to their normal set points. Air conditioning comes back on 100% power to try to catch up now that it's had all that time where it's not been able to maintain space temperature. And then all the interruptions cease to be interrupted and things resume to normal operation. So immediately after the demand response event, your demand jumps way up. And it jumps up higher than what it would have been had you not done the demand response at all. So that's what snapback is. And it's also called rebound in some publications. It usually lasts for 1 to 4 hours after the event. It can even go into the next day sometimes. One study in California found that it actually lasted over the next day. But that's uncommon. Usually it's in the 1 to 4 hour time frame. And something interesting we found when looking at the data we had was that almost all the snapback effect comes from residential customers, as you will see here in the graph. First, before we get to that graph, this one here shows the system load after an event. So this is from our data showing the last few hours of the day, as you see, hour 22 through 24. And the blue line is what it would have been had you not done demand response, and the green line is what it actually was with demand response. And as you can see, it's kind of hard to see, but the green line does pass over the blue line, and that region right there is the snapback. And then here's the graph showing the breakdown between residential and commercial, industrial. Obviously, most of the snapback, 91%, comes from residential. And the question, of course, is why does that happen? And so in order to address that question, we wanted to look at the residential sector a little bit more carefully. And we'll get into the details of how we did that, but first a little bit about what they do at the residential side for demand response. One way that's common is to use air conditioner electric heat cycling. And that's where you do 15 minutes on, 15 minutes off, typically, is the cycling that they do during an event. Then you have domestic hot water curtailment. That's where you just simply turn off somebody's water heater during an event and use thermal storage built up in the water tank to allow the customer to continue to have hot water while saving the energy of the heater. Then you have electric thermal storage using ceramic blocks with electric heaters in them and fans. And this stores up off-peak electricity to use as heat the next day during the peak. And then ice storage, where you run your chiller or your direct expansion unit overnight and store up a giant block of ice, basically. And then during the day, you run refrigerant through that ice block and use that to supplement or replace the compressor during those peak hours. So these different things, demand, energy, snapback, demand response, how do they relate to each other? And how can we quantify that? Well, first of all, demand response saves demand. That's its purpose, primary purpose. And the large utility that we studied in 2007 saved 454 megawatts of peak power by doing demand response. It also reduces the utility operating costs because of the high cost of electricity that's on peak and the high cost of generating electricity on peak. You save money for the utility. It also, and that going along with that, of course, the generating efficiency increases as you reduce your peak generator operation, since they're the lowest efficiency generally. And it causes snapback in residential customers primarily. And demand response also saves net energy. It actually, in addition to saving demand, our data show that it saves energy as well. These are some numbers from the source and source savings per event, per demand response event. from our data in 2007. And then this down here, this has been normalized by the megawatts of customers participating. And this is the customer side savings. So it's not completely unsubstantial, and it's something that should be considered. And where do all these energy savings come from? As we talked about, 91% is residential, and commercial industrial, however, represent the largest loads on the system. But our hypothesis is that commercial industrial customers have backup generation or are often unoccupied by the 7 or 8 o'clock hour when the demand response event ends. Therefore, they don't see the same snapback that residential does. But because they contribute so much of the demand reduction during the event with no snapback, they represent the largest chunk of the energy savings associated with demand response. And with the resident, and as I said, they don't have much snapback to cut into that savings. And there's an example showing a typical demand response day for one utility, baseline load, what it would have been without it. The green is the actual with demand response, and all that area in between the two curves, that's savings. And actually, you can't see it because it's really small, and I zoomed in on the slide earlier, but the snapback shows up just a little bit at the very tail end of that. So before we started our own research, we looked at what was out there as far as snapback, quantifying snapback, and demand response energy savings. So there's a few studies out there. Some of them did better jobs than others of looking at snapback and quantifying. And so, you see some of these did, California did a few studies, but I was underwhelmed with the results, particularly because they had graphs that would show snapback in them in their appendix, but they didn't address those results at all anywhere in the report. So they didn't seem that snapback and the energy impacts were important to them. They were more concerned with demand reduction, which is certainly understandable. But given that in these studies, a few of them quantified snapback, but generally that was not the focus of the research, and certainly seems like there was a lack of research out there to compare to. Certainly in some of the other technologies that we will look at here later that hardly anyone has looked into. So these are the largest studies that we compared to. And this table here, I know it's big and complicated, but primarily I wanted you to focus on this column here. This just gives you an idea of what the demand reductions that these studies found for these different types of demand control. You have air conditioner controls, you have water heaters, more air conditioner, water heaters. Obviously those are the most common, so those get the most studying. One study did electric thermal storage, and most of them did not look at snapback, quantify it at least, as you can see in this column. And most of them didn't look at energy savings. There's only a couple that actually did quantify the energy savings of these different demand response technologies. So there's clearly some information lacking that we wanted to try to fill the gap. And so for the DER study that we did calculate the snapback and the net energy savings for demand response. We looked at two different utilities. One was a large investor-owned utility, and the other one was generation transmission co-op. We looked at their system-wide load profiles on those demand response days, the baseline curve, which would have been what they would have done without demand response, and then the curve with demand response. And we looked at these 5 individual demand response technologies, and we wanted to analyze those each in detail at the individual home level. So we looked at 2 different utilities, like I said. These utilities were pretty different. They had different generator mixes, different mixes of customers, residential versus C&I, different numbers of customers. So the two utilities were separated for analysis purposes. Our data had 8 demand response events from the IOU and 21 from the cooperative.
Why was there such a difference?
That's a really good question. Well, one reason was they're different years, so the weather was different between the 2 years. One was 2007, one was 2011.
So why did you use the same year?
Unfortunately, that's the data we had available to us. And because we were able to keep them separate, we were looking at them as separate entities, not so much interested in comparing the two.
Are all of your events in the summer months?
Yes, all the events that we had in our data were from the summer. We did not have any, unfortunately, we didn't have any winter data to look at.
It just seems interesting because drawing conclusions from 21 versus 8 there's a big difference there.
Sure, sure.
Yeah, I'm not a statistician, but
Yeah, no, and we would have loved to have more, and obviously the 8, because the IOU's loads were much higher, so there's just a lot more, they had a lot more customer base too, like 4 or 5 times higher.
Were both of the utilities summer peaking? Because I know sometimes co-ops can be winter peaking.
Yes, yeah, both were summer peak, yes. The co-op was large enough that it actually still had enough, suburban or city customers, industrial customers to drive that up. So we aggregated all the events from that year into one average or typical event for that year. And we developed system hourly load profiles for that typical event. And then we used we calculated the per event savings using the generator efficiencies, distribution losses, and load profiles for each of the utilities. And you'll see that here. So these are our final results for our utility scale analysis for the 2 utilities we looked at. And you could see the load relief, the source savings, and then these 2 here, the 4th and 5th rows in the table, are normalized by the megawatts of customer enrolled in that demand response program. So that was in order to normalize it to make it more useful more generally. And so those are the normalized values for these 2 different utilities and the net energy saved for each. This is for that typical event. And so let's see, then next up, I'm going to discuss a little bit how we did energy modeling to look at the energy savings at an individual home level from these different demand response technologies. How do homes and home air conditioners and home water heaters interact with demand response events? So we took a typical Minnesota house. We used census data along with energy codes to define what a typical house is. We also utilized a previous project we had done for DER on geothermal, and we utilized that same model house with just a little bit of updating. And we used Energy Plus and BE-Opt to do the actual modeling. Energy Plus did all the energy analysis. BE-Opt is just a software it's designed for residential modeling, and it makes inputting residential parameters and designs much easier than Energy Plus by itself. So it works with Energy Plus. And we use that to simulate demand response events on, we chose peak summer and winter days. And we did 3 different home sizes. We were comparing the no demand response demand and energy versus demand response demand and energy the same day, the same hours. We did 3 different sizes: a small house, a median house, and I use median there, and that's from the census data, what the median house for the Twin Cities metro area was, and a large house.
do you know what the definition of that was?
I have it in here, I believe, coming up. Yeah. But, 3 climate zones. These are the 3 climate zones defined by DER for the state. So we have Minneapolis representing Zone 3, St. Cloud for Zone 2, and Duluth for Zone 1. And then we had to develop custom models for the ice storage and electric thermal storage because those could not be incorporated in any of the energy simulation models. And so we developed spreadsheet models to analyze those. This is, once again, really big table, but this is, if you want to read the report, you can look at these in more detail. But these are these are from the old geothermal study, the first 2 columns. And we adapted the large and small house from those to use for this project, and then we added the median house over here. So there's your, 2169 square feet, 2-story, other things like that come from that. So that's where we got all the parameters, the windows, the insulation, etc. For the energy modeling. And these are the results from that research. And as you can see, we get savings for everything. The only thing, thermal storage does not really produce energy savings, because electric heating, whether you do it off peak or on peak, or whether you do it when it's cold or warm, the efficiency does not change. Unlike cooling, where if you do it at night when it's cooler to store up, like an ice storage, you can save the efficiency of the compressor is higher at night. That is not true with electric thermal storage, so therefore you don't get any energy savings, but you do get that peak demand savings still. You're just trading off electric heat one time a day for another, so there's no energy savings associated with that. But these other ones do. It varies in degrees. This is for the Twin Cities, so with that weather data. And circle these first two here because these are, I wanted to characterize the snapback, obviously. So I included that here, but this is the net. So this includes that law. You lose some of the energy you save during the demand response event with the snapback after the event. So this takes that into account with the net values here. And this is per event, per house. And so we're going to look a little bit more at some of this data here. So these are the results. The first graph in the upper left is home size. And more or less, you see the trend that you'd expect. You expect the savings to go up with a larger house, has a larger air conditioner, larger heating, a larger water heater, etc. So more or less, it does follow that pattern. It's not perfect, but that's more or less what we saw. And then with the climate down on the lower right, it kind of, it's a little surprising, some of the stuff, but you would expect the air conditioner savings to go up as you get to a warmer climate. Though of course Duluth, there just doesn't get cold enough often there to really trigger much air conditioning need in the summer. So I think that's why that one is so low. Electric heat, we think this had to do with the weather data, why it wasn't a nice, pretty. It actually should go the other way around. And I'm going to talk about that a little bit as well, about why Minneapolis was strange. But the rest of these are pretty much as you'd expect, nice little stairs. So let's see. Next, I want to talk about the ice storage. And so these units, basically the way these work, we looked at what are called Ice Bear units. This company called Ice Energy makes these. And they come in 5-ton increments, and you can attach them to an existing direct expansion rooftop unit. And basically it has its own compressor and its own storage compartment for ice. And then it has refrigerant lines that connect to an evaporator that you install into the existing rooftop unit. And then it allows you to exchange refrigerant between the ice storage and your main rooftop unit, and allow you to get that cooling by storing it up at night, and then during the peak afternoon, the ice storage unit kicks in and does all the cooling for you and relieves the strain on your rooftop unit. And so to model this, we want to look at a variety of typical small commercial buildings. So we looked at everything 2,000 to 8,000 square feet. We looked at we sized the units accordingly in 5-ton increments because that's the way these units are manufactured. So we did 5-ton, 10-ton, and 20-ton cooling loads. And we did the different schedules because we wanted to see the effect that building schedule would have with setback and everything. So we did 4 different building schedules for those sizes of building to represent 4 different uses: retail, a 24/7 operation, those sorts of things. And then the static pressure increase, the reason we did 3 of those is that when you install the additional evaporator coil into the rooftop unit, you actually increase the pressure that the fan in that rooftop unit has to overcome. And so that actually has a negative impact on energy savings with these devices. So, and there's a range, depending on the manufacturer of your rooftop unit, if it's York or if it's Carrier or Trane, they all have slightly different impacts. And Ice Energy, a company that makes the Ice Bear units, has studied this, and they found that they range between 0.1 and 0.26 inches of water in terms of the pressure increase that that fan experiences. So we modeled those three to get the full range, and we did it for all these different conditions to try to capture some sort of trend in how we can relate the energy saving, energy penalty, and demand savings with these different factors. And so here's the trends we ended up with. After running all those simulations, we found that the peak demand savings varies linearly very well with the cooling capacity in tons. And so we were able to develop a nice little profile for this range of cooling from 5 to 20 anyway. That worked out really well. The peak demand savings correlated well. And then when we looked at the energy savings, which is actually an energy penalty because it increases the energy use overall, we had to do a three-dimensional fit because there were two parameters that actually ended up being dependent on. It was dependent on the tons and the hours of operation schedule, which makes sense that the energy use should be dependent on both those factors. And so we did a three-dimensional fit for that to develop an equation that would relate those two parameters to the energy savings. And this is how we actually went about doing it. We used eQuest software to develop our cooling loads. So that's how we determined what the cooling loads in the building were for every hour of the year. Then we used the manufacturer data provided by Ice Energy to get the ice charge times, how long it takes to store up the block of ice that you need to meet that day's loads during that peak hour, peak time of day. And then we use Ice Energy's compressor curves to get the compressor demand, and we calculate the charge hours per day, and then develop the correlations that I discussed. And as I said before, the energy increases because of the fan energy penalty. So these are the two equations that we developed based on this research. And as you can see, obviously, because it's a three-dimensional fit, two parameters, it's a little more complicated of a formula, but nonetheless, you get your energy penalty from that formula by inputting your hours of operation per week and then your tonnage. This is a graph demonstrating, what a typical day looks like on a typical peak day for an ice storage unit for one of these Ice Bear units. So this yellow line is what a typical rooftop unit does, just your standard rooftop unit. Before the building becomes occupied at 6 a.m. and it starts to cool the building down, so it has to turn on, and it cools it and peaks demand at 2 p.m. when it's hot outside, and then it drops its demand until it turns off when the building is unoccupied. What happens when you install the purple line here is the ice storage system. What happens here is the ice storage system is charging from about 1 a.m. until about 6. So it's charging, instead of using 0, obviously you're using about 6.5 kilowatts while it's charging up the ice. And then for 1 hour here, both the rooftop unit's compressor and the compressor in the ice storage unit are both running. So demand spikes here at 6 a.m. And then once the ice storage unit is all charged up, it's got all the ice it'll need for the day, it turns off, and now your rooftop unit takes over for the next few hours until you get to the peak time. And you can set that. In this case, peak starts at noon. So at noon, the rooftop unit shuts off, and instead you start using the ice storage unit. And the ice storage unit, to discharge that block of ice, all it needs is a pump and a fan. So it's only using about 300 watts power during peak demand time. So you see that big reduction there, savings from using ice storage. And then, of course, as the day goes on, once you get off peak again, the rooftop unit comes back on. That's what these two are. The rooftop unit comes back on to meet the remaining day's cooling loads, and then everything shuts down again and start over. So that's kind of the process that the ice storage goes through. And the green line here is just to show you the outdoor air temperature profile for that day. This was August 27th. So now I want to talk about deemed values. We looked at these values already a little bit before, but I wanted to reiterate them. So these are for summer demand response events. And the intent here is to be able to let utilities match their customer base, their type of utility, their capacity, and other factors to one of these two utilities here that we did in the study to try to find the best fit in order to use these deemed values, these normalized values here, in order to apply them to your utility. And also generator efficiencies also are part of that calculation as well. So that's kind of the intent here, was to develop something that utilities could use that could relate, they could calculate their demand response energy savings and demand impact using this data. So in order to really help with that, we developed a calculator. It's an Excel spreadsheet and hopefully easy to use, and has all the instructions laid out. It walks the user through different levels of rigor or detail depending on the information that you have available at your utility. It's designed to help utilities identify the best system, the best system level demand response energy demand savings that fits their utility best. And so we're trying to get the most accurate number we can by having these different levels of detail. So I'm going to try now to launch this. I want to demonstrate the use of this tool briefly. So it starts here with question 1. This is asking if you have hourly load relief data. So that's the type of data that we used in our study that we got from those two utilities, where they had a baseline profile, which they usually develop using some sort of regression model, determine what their load would have been if they hadn't done demand response, and then the actual load profile for that day with the demand response. So if you have that hourly data, that's great, and then you could just say yes here, and then these blue arrows are pointing you to where you put that data in. If you say no, so maybe smaller utilities, municipal utilities may not have that kind of level of information, then you can move on to step 2, and you can look at these two utilities, look at some information, and determine which one better fits you based on that information. Which of the two utilities used in the study best match yours? And then down here you also need to add in what your capacity is, because these are normalized values. You need to know how many megawatts are enrolled in the program. And then you can scroll down here again, and this is to further hone those numbers. You know, if you have this information, then this really helps improve the accuracy. If you have your peak load or generator efficiencies, your weighted average efficiency, and your average demand response event length, you could type those in and put those. That will help increase the accuracy. And then these are whatever your results are show up down here. You get your source savings and your demand side savings per event for your specific utility. So hopefully that's a useful tool to use and help to make these results kind of more applicable. I want to just briefly touch on some of the limitations of this research. The residential results relied on energy simulations, so we didn't have field data necessarily on individual homes to validate with. The ice storage modeling results are limited to that range because statistically we can't go beyond that range reasonably, because that was the range that the modeling was done on, the 5 to 20 ton range. But we think that that covers a pretty large range of small commercial buildings. Heating and cooling results are climate dependent. These are all obviously done all in Minnesota. You know, California or someplace else probably wouldn't be able to use very much, particularly the residential results, because those were very dependent on weather. The study is intended to be a starting point for snapback research. There's not a lot out there, like I said. especially about quantifying it and coming up with actual numbers people can use. So this was an attempt to start doing that and get some numbers people could actually start using and analyzing their own systems with. And obviously a specific impact study for your utility is going to be better, when you can actually do meter data and things like that. But in lieu of that, this is something that can be used. So I wanted to end on this with the potential for demand response. So it does save energy as well as demand. So I think that sometimes gets lost. So I want to make that clear that demand response definitely has energy savings potential. There's a lot of potential out there that is being untapped. DOE here says that 44% of commercial buildings use packaged units, use DX units on rooftop units. And yet, I've never seen an ice bear unit out in the field, and I don't hear much about these type of units. Whether it's ice bear or some other manufacturer, they're the largest one. Why isn't ice storage used more often? How much potential there is? 44% of buildings, there's definitely some potential there to look at responding to demand effectively, particularly because cooling is such a huge portion and contributor to peak demand. So I think there's a lot of potential for ice storage there, and also Snapback is almost all residential. So that's where you should expect to see Snapback occurring, but it's still dwarfed. Even on a residential level, it's still dwarfed by the energy savings in most cases. So even though there is that Snapback present, you still end up with net energy savings for the event. And there's cost, demand, and energy savings potential for both utilities and customers with all these different demand response technologies. It's definitely a valid investment to look into. So with that, I'll open up to any questions and point out that the report, Demand Response and Snapback Impact Study, which this presentation is based on, will be made available by Minnesota DER sometime in the near future. So thank you.
We have 2 of the ICE units in Austin on our public schools. If you're ever interested in
Okay.
seeing them.
It's interesting. Yeah, I did not, I wasn't aware of that. Yeah, the ones I read one case study they had was out in Anaheim, California. But yeah, I did not know that. Austin.
One's a brand new building.
I just wanted to point out quickly that the report actually is already.
Oh, it's already available. Okay, thanks, Joe.
On the website. You're so efficient, Jeff.
I didn't want to say that and then have you look at me like,
Yeah.
oh, well, no, it's not.
So on the
Yeah.
Snapback on residential, is that assuming that the entire load available for interruption is interrupted at the same time? Because I know we cycle them.
Right. So, yes, on the individual home here, I cycled them 15 minutes on, 15 minutes off in the simulation. So I simulated that cycling for that one house. Now, obviously, you're going to have staging where you have some houses, on while the other ones are off, and vice versa. But yeah, for the individual home modeling, I did that. Of course, the system level data would include all those effects. Yes.
That ice storage system you're talking, do you actually remove cord from the refrigeration unit? So let's say a really warm day, beyond capacity of our ice storage system, we need to run the rooftop units.
Yeah, they actually operate simultaneously often. Sometimes they'll just use as a booster. Like if you need extra capacity, then use ice storage just for that. Not necessarily to completely replace the existing unit.
We, like Kelly, have a couple schools, and we had really warm days in September, and they had to supplement basically with their rooftop units, and it really increased demand, actually more than anticipated. So I was wondering if you were anticipating controlling.
Well, in my analysis, yeah, I assumed that you could offset all of it, but often, that's not the case. Maybe, it's cheaper, obviously, to buy less capacity, not meet all of your capacity with the ice storage unit. And yeah, obviously, you wouldn't see the same demand savings if you're only going to offset part of it rather than all of the cooling load. Hopefully, you'll still see some by storing it at night and not getting it off peak electricity, obviously. Yes.
So my understanding is, right, there really is no PWH savings, so they're really looking on peak savings.
and no incentive allowed by the SIP program in the state?
Well, I'm not familiar enough with that program to comment necessarily about how that would work out. Often these are ice storage units are often used, utilities will often actually even own them at the customer site. And so it's really for the utility to get the peak load reduction rather than customer. But you can, it depends, you can arrange it different ways. Sometimes the customer can get credit for that demand reduction. I'm not quite familiar enough with that program to specifically say about that.
I think that's something we can take a look at. So, it might be something that would be useful to have in our here on your smart grid provider. We help folks to calculate the impacts from ice storage units, even if they're not, there's no energy savings.
Yes,
Kind of playing off the previous question here, did you look at the cost impacts? Because like with the ice storage, if for instance you weren't on a peak off-peak demand rate and you set a peak with the ice storage, you wind up having a cost impact because of that.
right, and actually that was beyond the scope of the study. So yeah, we didn't look at costs at all. But yeah, that would be good to look at too, an initial cost and then the operating cost associated with these. Yeah, well, I didn't look at that particular part of this.
So you're saying that 91% of the snapback effect is residential.
Hmm.
And that, is that proportion reflected in the demand savings from the demand event or the demand response event, or is it mostly a commercial savings?
Yeah, it's the opposite. The opposite is true. I mean, I don't remember the percentage off the top of my head, but commercial industrial is the vast majority of the during event savings.
Okay. And then, forgive my ignorance here. So is that mostly, so in the residential setting, it's essentially demand responses, HVAC and water heating, you said?
Yeah, primarily.
And in the commercial industrial, is there a lot of process savings? They shut down?
Yes, either they shut down or they go to backup generation capacity, or they shift production around, whatever they need to do during those interruptible days. But yeah, that's where they got all those machines coming offline, saves all that demand. All right, I guess that's all the questions. You guys want to turn it back over to you?
Sorry.
Oh, go ahead.
One question.
Yeah.
How many houses were included? Because you were looking at actual data for the residential snapback effects, right? For the
Yes.
when you're breaking down the models of the different regions in the state, right?
Yeah.
How many households were included, in the water heating portion of that? Do you know that number?
In the system level utility data?
Yes.
I have those numbers in the report.
Mm-hmm.
Yeah, it's hundreds of thousands.
Okay, that's a big sample.
Yeah.
Okay.
So. All right.
Thank you very much.